Hello everyone, this is Lingduo, and this video will give a brief introduction of Xmon superconducting qubit. Quantum computing is the use of quantum mechanics to control the time evolution of quantum states with special phenomena in physical hardware for computation and simulation. Quantum supremacy is the goal to prove and demonstrate that quantum computers can solve problems that are beyond conventional classical computers' feasibility. Since the 1980s, the theoretical study of quantum computer science has been developed well. However, the coherence, connectivity, and control of qubits become a problem that cannot be ignored when building the quantum computers. Superconductivity became a candidate platform since it allows the electron condense into a macroscopic quantum state. Each of these states can be controlled individually, and they can integrate into large quantum circuits. In 1985, J.M. Martinez described quantized energy levels for microscopic variables based on current Josephson junction, and the position of the energy levels was agreed with quantum mechanical calculation. From then, lots of research has been done in superconducting qubits field, and large-scale superconducting quantum systems become more and more practical from engineering point of view. However, there are still some effects that may demolish quantum coherence in superconducting circuits, such as material defects, electron system excitations, and radiative coupling to external wiring. To minimize these and other effects, in 2007, Koch introduced a new type of superconducting qubit called the Xmon qubit. The Xmon was designed to achieve much longer coherence time by significantly increase the ratio of Josephson energy to charge energy, and this design leads to low sensitivity to charge noise. Later in 2013, Barron's demonstrated a fully planar, Xmon-based qubit, which combined simplistic fabrication, straightforward connectivity, fast control, and long coherence, and it was named Xmon qubit because of its cross shape. As its name indicated, Xmon qubit has 4 arms, and its 4 arms connect to elements with different functions. As shown in Figure A, a readout resonator coupled with a waveguide is on the top, a quantum box resonator on the right in order to mediate between other qubits, XY control on the left to excite the quantum state, and Z control on the bottom to tune the qubit frequency. The cross is the qubit capacitor, connected at the bottom to the tunable Josephson junction, which is formed by the rectangular ring-shaped superconducting quantum interference device, which is also known as squid. 3 of the connections are easily accomplished with a capacitor, by coupling each of the qubit's arm to a distinct element, as the qubit is connected to ground. An advantage of this approach is that each coupling can be tuned and achieve a specific function individually. And the reason for Xmon to achieve better performance is the large ratio of the Josephson energy to the charge energy, since there are 2 quantities that are important to Xmon qubit, anharmonicity and the charge dispersion of the energy levels. A large anharmonicity is needed to prevent qubit operation from exciting other transitions in the system. The smaller the charge dispersion, the less the qubit frequency will be influenced by gate charge variation. The magnitudes of charge dispersion and anharmonicity are both determined by the ratio of the Josephson energy to the charging energy, EJ over EC. The charge dispersion declines exponentially in EJ over EC, while the anharmonicity only drops algebraically in EJ over EC. As a result, we can greatly limit charge noise sensitivity in the qubit, while only sacrifice a small amount of anharmonicity by operating the Xmon at a much larger EJ over EC ratio. The equation shows that through plugging in the additional capacitance Cb, the charging energy can be made small compared to the Josephson energy. The lower figure are eigenenergy of the qubit Hamiltonians and function of the effective offset charge, Ng, for different EJ over EC. From the figure, we can clearly notice that the total charge dispersion drops very rapidly when EJ over EC increases, and that the level anharmonicity, though decreases at the same time, is still large enough for selective control of the transition. The table lists qubit families and different values of parameters. EJ0 over EC describes the number of charges, and EJL over EJ0 represents the flux types of devices. For fifth qubit, the large area of junction oxide gave rise to minor defects, trapping two-level fluctuators that limited the coherence time severely, so the coherence time is less than 1 microsecond. For RF squid qubit, since its inductive squid loop is large, the flux qubit is sensitive to flux noise, and the relaxation and coherence time are quite short. It's around 20 nanoseconds. And for flux qubit, the coherence time also has not improved much, which has so far been a main limitation of its applications. Presently, the C-shunt flux qubit shows promising prospect, with broad frequency tunability, strong harmonicity, high reproducibility, and coherence time in excess of 40 microseconds at its flux insensitive point. Xmon qubit, which also has long coherence time, is now used as a central component of several scalable platforms, and successive generations of IBM-Q processors have demonstrated the capacities of superconducting transmon-based qubits working as a basis for electronic solid-state quantum computers. Xmon, which is a variant of Xmon qubit, basically shares the advantage that Xmon owns, and from the table we can tell that, compared to Xmon qubit, Xmon qubit has larger shunt capacitance. Also, since Xmon is designed with 2D array architectures, it can easily be coupled to near its neighbor qubit, and Xmon is floating while Xmon is grounded. Since Xmon was introduced, it has been one of the leading platforms for quantum computing, and lots of efforts to improve qubit lifetimes have been made. In 2020, Alex Place fabricated a two-dimensional Xmon qubit that have both lifetime and coherence time with dynamical decoupling exceeding 0.3 milliseconds by replacing the material with tantalum in the device. These results pave the way for higher gate fidelity in multi-qubit processors. In 2019, Zhong demonstrated the deterministic violation of a Bell inequality in a superconducting quantum communication architecture, using a pair of superconducting qubits coupled through a 78 cm long transmission line, with photon emission and capture rates controlled by a pair of electrically tunable couplers. For previous research, the main strategy for enhancing the dephasing time in superconducting qubits is focused on quantum circuit design and eliminating the linear noise sensitivity by operating qubits at optimal working points. And there is second approach, by improving the property of junctions and materials to eliminate sources of 1/f noise. It is a difficult and costly process, but it is likely to benefit a wide range of qubit design when it is successful. In the long run, a combination of both strategies will probably be necessary to realize a scalable design for superconducting quantum computing. And the limit of T2 equals to T1 has not been reached, indicating there is additional dephasing. The reason for this, as well as dephasing away from the flux insensitive point, still need more investigation. Lastly, although the name Xmon emphasizes its cross-shape, more arms can be added to allow for more connectivity. That's all. Thank you for listening.